that? No, in the other one? No. Okay. Can you put it so I can see?
Let me check.
Yeah.
Oh, it is, I think it is that way.
Yeah, okay, that way. Perfect.
Super good trousers.
Oh, all is set up.
Very professional now.
Yeah. Up. Okay. So, up. Perfect.
Okay, thank you everyone for joining. So as usual, we have part of our audience who is in here and part of our audience who is following online through the KU Leuven streaming service. And so today we are happy to welcome Léa Planquart from the University of Brussels, of the ULB. She is a first-year PhD student, and she is working in the group of Alain Jorissen, and today she will actually focus on one particular star, the star V Hydrae, and so she specializes in spectroscopic binary HGB stars, and that's what will be the topic of today. So please, Léa, you have the floor.
Thank you very much for this introduction and for letting me the opportunity to share my work. So as Joris explained to you, I will speak about spectroscopic binaries among HGB stars and focus on one particular star known as V Hydrae. So before entering in the table of content of my talk, let me just remind you what an HGB star is, because it's the main object of this talk. So the HGB star, you may already know, it's an evolutionary phase for a star having low to intermediate mass, so between 0.8 and 8 solar masses. The name comes from the fact that the HGB star phase is asymptotic to the red giant branch in the HR diagram, so luminosity against temperature. At this stage, the star is made of a 9 coat of carbon and oxygen and have two burning layers, one of hydrogen and one of helium. But the most important observational characteristic of the star is their pulsation. In fact, we can see in the light curve and in the radial velocity curve of the star a variability which is due to the pulsation of the envelope. So as the star, for example, here you have an example of a light curve of an HGB star, where you can really see the periodic pattern of luminosity at 300 days, which is due to the pulsation of the envelope of the star. The period typically ranges between 10 to 2,000 days, so they are known as long period variable, LPV, and they are classified according to the regularity of the pulsation. So Myra being the most regular, semi-regular, or irregular variable. So now that I briefly recall what an HGB star is, what is the motivation of my work, and therefore the subject of this talk, is to find binary system among HGB stars. So why are we looking at those kind of objects? Because binary configuration, when an HGB star is in a binary configuration, the binary system will influence the property of the HGB star, for example, the geometry of the massless. So it's interesting to know the existence and to parameterize those systems. But unfortunately, it's quite difficult to find that kind of system, and mainly because due to the pulsation, the radial velocity curve will be polluted by variation due to this pulsation. So usually, when we want to find spectroscopic binaries, we are looking to an orbital Keplerian signature, but due to the pulsation of the star, the radial velocity will be polluted. So the idea here is really to disentangle the two signals, the pulsation from the orbit signature. To do so, we have at our disposition 10 years long of radial velocity monitoring of 16 HGB stars with a binary suspicion, so mainly in literature indication that the star could be in a binary system. So if you get the chance to observe at Mercator, those stars were part of program 10, so maybe you have observed one of the stars that I have shown here. So as I said, the main part of this talk will be focused on the carbon star V Hydrae, because we found an orbital, a good orbital solution for those stars, and also some other particularities in the spectral line. So first, I will go into the method used to disentangle the two signals, so how to disentangle the orbital signature and the pulsation. So as you may know, the radial velocity monitoring came from the Hermes spectrograph, which is located on the Mercator's telescope. That's how he looked the last time I saw him. And here you have how we obtain the radial velocity. We obtain it by simply Doppler shift of the spectral line. And by this Doppler shift, we use the cross-correlated function. So the cross-correlated function is a technique allowing to have precise radial velocity by simply convoluted a synthetic spectra with the spectrum of the star. And therefore, we can obtain, for example, long-term precision up to 70 meters per second. So thanks to that, we can have radial velocity. And if we monitor the radial velocity for spectroscopic binaries, the curve of the radial velocity curve is supposed to follow the Keplerian orbit, and therefore to be governed by the Keplerian equation that we can see here, which is a transcendental equation with link to the orbital parameters, such as the eccentricity or the true anomaly of the orbit. But if we have an EGB star in a binary system, the star will follow the Keplerian equation plus another function that we have to fit to take into account the additional variation due to the pulsation of the star. So we decided to fit the pulsation with this function called asymmetric sine function. So that's the mathematical form, but what is more interesting is that it is simply a sine function with an additional gamma parameter, which allow to tilt the sine function upon the left or upon the right. And that's interesting because it will really reproduce the variation that we can see in the pulsation of the star. So finally, the final function that we have to fit to our radial velocity monitoring is the sum of the two. So the function for the orbital motion and the function for the pulsation. So it's a complicated equation made of 10 parameters that we can fit with the least square routine. But this function, as it has a lot of free parameters, is really sensitive to the initial guess, the initial value that we will give for those parameters, and especially for the two periods that we have to take into account, so the orbital period and the pulsation period. Therefore, we need an initial guess for those two periods in order to apply the fitting routine. And to obtain this initial guess, we will do a preliminary frequency analysis using two data sets, so the radial velocity curve, which is a 10-year monitoring, and also a frequency analysis of the light curve, because the light curve we have a long spanning, about a century of observation, and we know that, for example, the pulsation is visible in the light curve. So that's the method we will apply. As you can see here, you have no way to see if the orbit is reliable or not. So before doing this method, which will give us an orbit for each radial velocity monitoring, we need to check which star of our monitoring will give a reliable orbit. So here, for example, you have our 16 targets, and to select the reliable candidate, we will follow the classification from FAMI on M-giant binaries. The idea of this classification is to plot the star in the diagram the following diagram. So we have plot the standard deviation on the hypercross magnitude against the standard deviation of the radial velocity from Hermes monitoring. So that's the value here. And this pink line is the threshold found by FAMI to select the single star from the binary system. So single star are supposed to be below the line and binary system above the line. So from this plot, we can select, so flagging the star if they are above or below the line. And we will only think that the orbits are reliable for stars that are located above the line. But that's what we can also do with this diagram, is when we compute, when we fit our function to the radial velocity from the star, we can remove the orbit that we have computed, and therefore obtain the standard deviation after suppressing the orbital motion. And normally, and you will see that it's exact, the star, when we remove the orbit, will fall below the line. So all the stars that were above the line fall below the line. So because we remove the impact of the orbit, and we have always, we still have the pulsation, but the stars are not in a single configuration like that. And the last column here on this table is the standard deviation after removing the pulsation and the orbit. So that's the residual value. We can see that it's in the range of 1 kilometer per second. So that's less, quite less than what we have at the beginning, but it's larger than the instrumental uncertainty. As I've said, the CCF has a precision of about 70 meters per second, and here we are with a value about 1 kilometer per second. So one explanation of this high value for the residual is the presence of convection. So AGB stars are stars that are supposed to undergo convection, and so they have a presence of giant convective cells that will induce radial velocity variation that we do not take into account in this fitting procedure. So that will pollute the residual value. I can show you two examples of fitting. For example, the star Air Crateris. You can see here the monitoring, and the bottom panel is the residual value, ranging between 1 and -1 kilometer per second. And you can see the orbit, and the orbit plus the pulsation that is given by the dashed line. And this procedure allows also to disentangle the two signals. So here we have only the pulsation. The star pulsates at 160 days, and when the pulsation is removed, where we can see the orbit. Another example is the star V Hydrae, that I will expose you later in more detail, where you can see that with the Hermes monitoring, we can really see the pulsation at 500 days, plus a long-term modulation. And so we can disentangle those two signals and obtain the orbit, and the orbit on that plot and the pulsation on that plot. So as I said, for the rest of this talk, I will focus on V Hydrae, because it's the star we study into more detail, and especially in the beginning of my PhD. So the rest of this talk is structured in three parts. So the first one, I will briefly introduce a literature review of all the observation of V Hydrae, because the star is well known from astronomers since a while, and we have a lot of different observations. Then I will go to how we obtain the orbital solution, and how we analyze the two data sets that we have, so light curve and radial velocity. And the final part of this talk is a discussion about spectral line variation that we found in that star. So let me introduce this particular star. V Hydrae is a carbon star, and which is at an advanced stage at the AGB phase. So here you have the star located in HR diagram, so luminosity against temperature. You can see that the star is at the AGB, and if we superpose evolutionary path to that diagram, you can see that the initial mass of the star is about 4 solar masses. We can also look at the SED of the star, And from the SED, we can see that we have an excess in the infrared. So, for example, here in pink, you have a synthetic SED. The red dots are the data from V Hydrae. And we can see that we cannot fit all the data with one synthetic SED, but well, with one synthetic SED plus a black body, which is an indication of the presence of dust, a dusty environment around the star, which is quite common for a star that has losing a loss of mass. And another particularity is the presence of a UV excess. So an AGB is not supposed to emit in that kind of wavelength range. So this presence of a UV could be an indication of a companion or in an interaction with a companion. As I said, V Hydrae is an advantage stage of the AGB phase and shows also indication of a transition to the planetary nebula phase. For example, the star has wind component, see in the CO rotational bands. So that's an indication, for example, of transition to planetary nebula, because at that stage, the star have a wind component. So we have 3 wind components. So here you have a schematic view of the environment, allowing to distinguish the 3 wind components. So we have a vertical bipolar outflow, really fast, denser equatorial CO outflow, and an isotropic, slower velocity wind. So we have 3 wind components, but more surprisingly, Sai and his team show also the presence of bullets. So by bullet, I mean high velocity collimated emission in the forbidden line of sulfur and iron. So these bullets are represented here by the blue and red point. So they are coming toward the observer. And what is really impressive with that bullets is that when Sai and his team monitored the bullet, they were able to track them and to reconstitute their temporal evolution. That's what is done on this plot. You have the time here and the offset from V Hydrae. And what they show on this plot is that a bullet is emitted every 8 years. So the first one in the 80s, the second one 8 years later in the 90s in that direction, a third one, and the fourth one. So they could distinguish 4 bullets, and each time the axis, the emission, flips up around its axis. So in that direction, then in the other direction, and so on. So that's quite strange, and especially the fact that those bullets are spacing by 8.5 years is difficult to interpret. And in their paper, they propose a model where V Hydrae was in a binary system, and that this emission of bullet was due to the passage at the periastron of the companion. So they propose a model where the orbit is quite eccentric, in order that at the periastron the 2 stars are really close, and with an orbital period of 8 years, such as this emission occur only once for 1 orbital cycle. I will show you later on that this model is not compatible with our observation. This was up until recently with one new paper that was published 1 month ago that where, again, Sai and his team image the large environment around the star. So that's quite impressive because using ALMA, they were able to image the CO band around the star. So it's a large view. As you can see, we have 4 arcs of scale. And they could image 6 expanding rings. So you can see on the picture that we can see 6 different rings, expanding rings. So they were coming from the star and extend. So they could model those rings. So first parameterize the 6 rings and model them under what they call disk undergoing dynamical expansion. Thanks to their model, they could simply age the ring. So the inner ring having an age of 200 years, and the more outer ring having an age of 2,000 years. So that's quite impressive. And also, with this imaging, they could again see the presence of a high velocity outflow in the larger environment of the star. So this diagram shows on the left panel the blue shifted velocity, and on the right panel the red shifted velocity. So we can see two kinds of outflow: really collimated outflow, so the red point here with the green filament, and also a wide outflow, which are shown here with the Dutch parabolic shape. So wide outflow here and wide outflow also in the redshifted part. So that's all for the observation that we can see in the literature for the star. So as you can see, the star have really a rich environment. And now I will go to our computation of the orbit of the star. So first we can look at the photometric analysis of the star. So as I said, for our routine, in order to find the orbital motion from the radial velocity, we need initial guess of the period. So what we can do is to look at the radial, at the light curve of the star. So here you have the light curve from the Association of Variable Star Observer, which is about 1 century. So this long spanning allows us to see the long pattern on this light curve. So here you have the Lomskargol periodogram of the light curve, where you can really see two peaks. So this peak is associated to the pulsation at 500 days, and a larger one at 6,000 days, so 16 years, around 16 years. Those two are aliases, so not important, not have to take into account. So these two periods can be used in our fitting routine as initial guess in order to find the orbit. Also to be noticed, if we remove those two variations, so the long-term variation and the short one, we can see on the residual value of the curve the presence of a third periodic pattern at exactly half of this long-term modulation. So now that we have guessed for our period, let's look at the radial velocity. Here is the raw radial velocity curve, where we can see that we have two kinds of observation. So in black, we have the observation where the spectrum give us, where for the spectrum we have one single value for the radial velocity. So here you have the shape of the CCF, which is a nice Gaussian profile. But for some point, always around light maximum, we have the presence of a double peak CCF. In fact, this double peak CCF is the result of the propagation of a shock wave through the atmosphere of the AGB. So at the light maximum, the star is at the maximum of compression, which gives birth to a shock wave that propagates through the atmosphere and as a result, we will have the presence of a red shifted peak and a blue shifted peak, which is represented by the couple of peaks in blue and red on this curve. For the fitting routine, we will simply remove the double peak in order only to fit where the value have a simple single Gaussian and therefore are more reliable. What I have to notice here is that we have a 10-year-long monitoring, and that the orbital period that we expect is 16 years long. So, as you can see, we cannot see an entire orbital cycle on the monitoring, only a long-term pattern. But fortunately, looking at literature, we found radial velocity computed by Barbone in the late, not really the late, in the 90s. And those values are really spaced from our monitoring, and we can add it in our fitting routine in order to obtain here the final curve, where in the continuous line you can see the orbit, And in the dashed line, you can see the orbit plus the pulsation motion. And here in the bottom panel, the residual value, which range between -2 and +2 kilometers per second. So from this plot, we can separate the orbit and obtain the orbital element, because the orbit is parameterized by its orbital element. So here you have the graph where you can see the radial velocity as a function of the orbital phase, and the orbital parameter that we have found. So as expected, we have a period about 6,000 days, so exactly the same as the period found in the photometric data, and which is twice what Sahai and his team have found. And also we have an eccentricity, which is quite low, and even compatible with a circular orbit. So what we can conclude from this is that our solution is not compatible with the work of Sahai, and even that the observations are not compatible with his model of 8.5 years, because our monitoring span 10 years, and we cannot see a full orbitized cycle. So it's kind of interesting, because as I will show you, this period is really compatible with the period found in the light curve, and therefore we can compare the light curve and the radial velocity curve. So that's what is done here. We have superposed in green the light curve variation, and in black the radial velocity variation, in order to see when happened the dimming event that we found in the light curve, that is found in the light curve. So you can see that the dimming event, so the moment when the magnitude is the highest, correspond to the moment when on the radial velocity curve we obtain a value of a 0 velocity, so the velocity equal to the radial velocity of the center of mass. And on an orbital motion, it corresponds to what is called a conjunction. So a conjunction is a specific moment on an orbit when the two stars are aligned for the observer. So that means that you have the two situations that are drawn here. We can have the inferior conjunction, when V Hydrae, the primary, is in front of its companion, and go from coming near the observer, and then go away from the observer. And the second situation is called the superior conjunction, so that's the opposite situation, when the stars go from going further to going nearer the observer. Here we can see that we go from red shifted value, so going away, to blue shifted value, so going nearer the observer. So the dimming event that we found in the light curve correspond to the superior conjunction, so this situation when V Hydrae is behind its companion. So the most simple explanation for the dimming event in the light curve would be that the companion simply eclipsed the star, but that's not the case. That's not really possible, because if we look at the shape of the light curve, here you have a representation of the light curve in a phase diagram, where each color corresponds to a different orbital cycle. You can see that first the obscuration is quite deep, so we have a decrease of in average 3 magnitude, which correspond to a decrease of flux of a factor 15, and also that the decrease is quite long. So when we fit it with a Gaussian, we can see that the width of the Gaussian is about 1/3 of the orbital period. So that seemed to be a really opaque and extended object that obscured the star at this particular moment. So one possible explanation, one idea that we have, it was that the star was obscured by a jet cone coming from the companion. So for example, here you have a representation of the star, V Hydrae in red, that is orbiting around the companion, and that you can see the jet cone coming from the companion, and the diagonal line is the line of sight. And you can see that at the superior conjunction, the cone obscured the star. So that could be the explanation of this extend and opaque obscuration that we found. So jet cone coming from the companion are a common phenomenon found in post-AGB star. And for example, in the work of Bollen, they showed signature of jet cone in the variation of the Balmer line. So we decided to look into detail in the Balmer line of V Hydrae, and unfortunately, we don't see any anomalies or jet signature. So here you have a spectral window of the star, each color representing a different orbital phase. You have to remember that V Hydrae is a carbon star, so we have a lot of pseudo-emission at different places, and the continuum here is not really clearly defined. We only take a mean value on this spectral window. And here you have the Balmer profile. So you have a little variation, and you can also see this small variation in this kind of diagram, where you have the radial velocity and the phase. So it's it's in the plane of the phase and the radial velocity. So blue shifted velocity corresponds to a smaller wavelength, and red shifted velocity to a higher wavelength. So this one is simply transformed into that diagram, where you can see molecular absorption here, molecular emission here, and those kind of blobs, blue blobs, represent the modulation of the H alpha emission, and you can see that this emission is only modulated by the pulsation. So here you have the orbital phase. The blank space is the phase that has not been covered yet by our monitoring, and in black you have the orbital motion that we have computed. So unfortunately, we do not see any presence of a jet in the Balmer line. But we can remember that the H alpha transition is a transition from the atomic number 3 to 2, so from one excited state to another excited state. So we need enough energy to see H alpha transition. It's about, I think, 10 electron volt to go to this third excited state. So an idea was to look at the resonance line. So resonance line designate a line where you go from the first excited state to the ground state. So we need less energy to go to that kind of line, and therefore to see that kind of emission or transition. So one resonance line, for example, is the sodium doublet. So here you have the spectral window showing the sodium doublet in the star V Hydrae. So same as the last picture, each color represents a different orbital phase, and the vertical line represents the laboratory value of the sodium doublet. And here you can see that the star undergoes some modulation of the intensity near the doublet. So for example, here you have in green, so around phase 0.5, molecular emission, pseudo-emission, that totally disappear as some other orbital phase. So we have a variation of this sodium doublet with the orbital phase. Another way to representing it is on this animated picture, where I also remind you the convention taken here. So phase 1 corresponds to the superior conjunction, so the dimming event and the obscuration, and phase 0.5 corresponds to the inferior conjunction, so when V Hydrae is in front of its companion. So from this, I will stop at phase 0.5, for example. Here you can see that we can see those two pseudo-emissions, typical for a carbon star, and then a deep absorption at the blue shifted value of velocity around -100 and -50 kilometers per second. Then if I go a little bit further in the orbital phase, and we stop at phase 0, at phase 1, you can see here the apparition of a pseudo-emission at lower blue shifted velocity. And here the two carbon lines that we have totally disappear, and we have an absorption around the highest blue shifted velocity. And we can see an intermediate situation around phase 0.2, where the two lines here begin to reappear, and here the emission decrease in intensity. Also to be noticed, when you look at the variation, you can see that the two lines here undergo small variation that are due to the pulsation nature of those carbon line, those molecular line. Here on those plot, it's always the same observation, but represented in a different way. So in the graph where you have the orbital phase against the radial velocity. And the color represents the intensity of the line. So in red, we will have absorption, and in blue, the emission. So for example, here, the molecular emission. We only look at the blue shifted part of those graphs, because all we are looking at is the absorption feature that we can find here and here. So first observation, we see quite similar pattern in the two doublet of the sodium. So this peculiarity that we found is really linked to the sodium transition. Also, we can plot it twice in order to really see the variation. So here I've take the data and duplicate the data a second time in order to see the variation with the orbital phase. And I recall you, the blank space is a phase where we have not observation yet. So what we can conclude from the sodium doublet is that we have a blue shifted pattern of absorption, which is with a modulated velocity range and a modulated, also a modulated depth. So it's deeper here than there, and also the presence of a pseudo emission around phase 1. So at phase 1 here and there, you have the presence of a pseudo emission. If we look at another resonance line and another alkaline metal, the potassium doublet, so the potassium doublet is really the same atomic configuration than the sodium doublet, we can see that for this this atomic transition, we can find the same kind of behavior. So here, you have again the two line of the doublet, two spectral window showing the two doublets. On the right part of each graph is the redshifted range of values, so it is not really interesting. You can only see molecular absorption and emission. But on the left part of the graph, here and there, you can see the absorption feature being larger at velocity around phase 1 and having a shorter range of velocity but deeper around phase 0.5. So again, we can see it twice in order to really see the pattern and the variation pattern with the orbital phase. So the idea was to explain this presence of the absorption pattern by the obscuration by a jet coming from the companion. And so the question is this kind of pattern giving us constraints of the geometry of the cone? So first to notice, we can see, maybe, yeah, it's clearer here, that we have absorption at all phases for the orbit. So all phases that we covered with our monitoring. So a first conclusion that we can draw is that the opening angle of the jet must be larger than the inclination of with respect to the orbital system in order to obscure at the superior conjunction, so when V Hydrae is behind the companion, but also at the inferior conjunction when V Hydrae is in front of the companion. If we have this condition, the line of sight will go through the jet, will border the head of the jet, and will also be absorbed at phase 0.5. And also, the configuration, the shape of our absorption, so most blue shifted at phase 1 and deepest at phase 0.5, will give us a constraint on the velocity and density law that we can find in that kind of cone. So just to give us a simple kinematic approach, we can look at the most simple model, the stellar jet. So a stellar jet, here you have a schematic representation of the cone. Each point in the cone is represented by its coordinate theta and z. We have that kind of law, velocity law and density law. So that's quite two simple law. And what does that kind of law say to us? First, the velocity is maximum at the center and minimum at the edge. So the velocity will follow this kind of behavior, being maximum at 0 and minimum at the edge, so at the angle 45 in that situation. And the density law follow an opposite behavior, so being really null around of the axis, and the density being higher at the edge of the cone. So in a sense, we have a hollow cone with high density at the edge and lower density at the axis. So with that kind of law, if we give to us two law, velocity and density, to each point in the jet cone and to each point in the line of sight that will go through the jet, we can compute the velocity and the density. That's quite useful if we want to reproduce the transmission through the jet at all orbital phase. So, for example, here we can compute this ratio that I have called the transmission, which gives us the amount of intensity that will go through the observer or being absorbed. So this ratio, we can compute it for each velocity at each phase of the orbital motion. So we have here this grid of orbital phase and velocity. We only care about blue velocity, blue shifted velocity this time. And you can see here the color map used. In red, we have absorption. So the transmission is equal to 0. So everything is absorbed. And in blue, ratio where the transmission is equal to 1. So everything being, nothing being absorbed. So we can see that kind of hourglasses pattern. So in order to give an intuition, I recall that at phase 1, so phase 1 at the top and the bottom of the graph, we have this kind of schematic situation. So the red dot is V Hydrae, and the line of sight goes through the entire jet. So we will have a large distribution of velocity, but high velocity. So at the center, we have a low density. So high velocity here, we have low density, and then a gradient of density up to lower value of the velocity, which are at the edge and really dense. And on phase 0.5, we have the situation where the line of sight borders the cone edge. So we will only have a lower value of the velocity, but a really denser ratio, so maximum of absorption. So what we can conclude from this kind of shape, if you remember, it's reproduced quite well the shape that we have found for the sodium doublet and the potassium doublet. So this kind of approach, using two simple laws of density and velocity, can give a good qualitative model of the absorption through the jet and explain the absorption pattern that we found in the line of potassium and sodium. But as it is written here on the graph, it's not really, we cannot take conclusion from that kind of work because we have numerous of parameters to fix. For example, here I have said that the inclination is a given value, the opening angle is another given value. So we have to fix the geometry, fix the density and the velocity law. We don't know if they are really physical. And we don't take into account any radiative transfer process. So this kind of model is interesting, but it's quite a toy model. So we need, in order to get some physical indication of the system, need to work on this model in order to have a better qualitative model, and not this quantitative model, and not this qualitative model. So that's where I have stopped my my work for now. So that's how the presentation will stop too. So I will finish with this take-home message. What have we found and what have I exposed here? I've exposed that we have found orbital parameter for AGB star. So we found spectroscopic binaries among AGB star, and we perform an in-depth spectroscopic study of V Hydrae. So we obtain a new orbital solution for this star, and we have studied the spectral profile of the potassium and sodium, and studied the scenario of a possible absorption by a jet cone. But what's next? The what's next in, I suppose, the rest of my thesis would be to model the radiative transfer to test the presence of a jet, to model really more the radiative transfer, and also to confront this result to explain the presence of a deep obscuration that we see in the light curve. So the decrease of 3 magnitude that we can see in the light curve, and also explain it in that context. So the final goal for this star is really to have a coherent picture that will encompass all the observation and put all the pieces of the puzzle together. But that's quite difficult because we have a lot of things to take into account, such as the ring, the orbit, the bullet, and the fast rotation, for example. So thank you for your attention. I hope I didn't speak too quickly. And if you have any question, do not hesitate to ask.
Thank you very much, Léa. Very interesting talk, very well explained. Are there any questions or possibly feedback that could help Léa? Let me start first.
Thank you for this very nice talk. I actually have a question about the obscuration event, and what is your current take on the interpretation on this obscuration event? Because it seems that you have the obscuration when the AGB star is far from us. Is that correct? Right?
Yeah. Yes. In fact, we have. Is it written here on the graph? We have the obscuration at SC, so at the superior conjunction. So when V Hydrae is really far for us, and when the companion is in front of V Hydrae. So our explanation is that this obscuration is due, in a sense, to the companion, but that cannot be due only to the companion. It cannot be an eclipsing binary, because the obscuration is too deep and too long to be explained by that.
So it really reminds me of the RVB phenomenon that is in post-AGB binaries, but it's reverse. So it means in some post-AGB binaries, we see that when the disk is inclined, when you have inferior conjunction, so the post-AGB star is obscured by the circumbinary disk because the disk is thick. But here, you say that maybe it's the jet that will obscure the AGB star, but it means that there is dust in the jet and that it's really optically thick. So it's, what would be your comment on that?
Yeah, unfortunately, as it's happened at the superior conjunction, it cannot really be explained by a circumbinary disk. As you said, it would be appearing at the inferior conjunction instead. So yeah, maybe our possible idea, but not explanation, just an idea, was to explain it by a jet, because in that sense, we will have an obscuration at the superior conjunction. So in any case, it must be linked to the companion passage because it's at the superior conjunction. So when V Hydrae is really far away for the observer. But we have to test it and see if it's compatible in terms of dust emitted from the jet to obscure so deeply and so long.
Okay, very, very interesting. Thank you.
I would like to make an additional comment to what Léa said. I mean, my feeling is that the absorption could be caused by the sodium atoms present in the jet itself, nothing related to the dust. That's right. Yeah, yeah, it's a lot. Yeah. Yeah. Yeah.
Thanks for the very nice talk. I have 2 questions, if I may. So one, possibly a follow-up to this discussion. What exactly is feeding this jet? So is there some sort of accretion that happens onto the companion? And the
I will answer to your first question first. So current explanation for jet coming from the companion, it's not that the jet is coming from the companion, but from the accretion disk around the companion. So that's the accretion disk that create this ejection of matter and that create the jet.
Okay, thanks. And the second question relates to the bullets that was found with HST. So these bullets, if you try to plot it in phase, do they happen at either inferior conjunction or superior conjunctions, or when exactly do they happen?
Yeah, if we plot the bullet in the phase, yeah, maybe I will, on this plot again. I didn't do it on this plot, but one bullet lay around this phase and one around this phase. So always, as they are spaced by 8.5 years, so half the orbital period, if the first one lay on a conjunction, every other will lay on conjunction 2. So the most recent one were emitted around the minimum of light, so around the superior conjunction. But there is an uncertainty on the time of emission because we don't know, we know the spacing from the star, but we don't know at its time exactly they were emitted from the star.
Okay, thanks.
Any more questions?
Thanks. So the extinction, so this plot is intriguing, of course, but I have another question on the pulsations, because you remove the jitter. If you have the diagram on the Famé
here?
Jitter? No.
Ah,
no,
yeah, I see.
In the beginning, yeah.
This
so,
one.
Yeah. How can you be below the curve?
Oh, okay. So
this I understand, but the other one.
Then I fit the curve, found the orbit, and then remove the fitting orbit from
no, I
the
understand.
value.
But physically, what does it mean if you are at like R Ursa Major? No, on the right. So
if you are, you mean here?
Yeah, and to the right, because the points, those points.
Those two. In fact, as I've mentioned, we deal with here a work that have been made on giant. Those stars are really star that cannot really be extended to this limitation. That's why the pink line, this pink threshold have a finite distance. So those ones, it's difficult to interpret them because we have hypercos magnitude which is really larger than what we would expect, and so they are not really in the range of our extrapolation of that graph. But for your information,
so they are more stable than what you would expect from.
No, in fact, those two stars as Myra with really important shock wave, the presence of shock wave. So maybe this shock wave induce really large variation in the Hipparcos standard deviation. I don't know if it's answer your question or if I didn't understand correctly.
But because your explanation was that it's so the residuals that you have is still larger than the uncertainty of the measurement. That means there is some jitter or some, let's say, residual which is due to the, and you call convection. But then I would, so that convective graph is then the pink line, but at some point it breaks down then, apparently.
Yeah,
so
all
the intrinsic jitter is only, you can correct for it, or you can estimate that just at only a fraction of the curve of that plot and not on the right hand side.
Yeah, exactly. Yeah, I cannot.
And do you know why?
No, I have no idea.
I'm co-author of the paper by Fame, so maybe I can comment. Actually, so this sample of M-giant binary is made out of, I mean, no Mira, actually, and it's consisting of semi-regular or irregular, or even, I mean, very small amplitude pulsators. And to the question about what does it mean to be below the threshold, it means that the threshold is the maximum radial velocity variation that we found for a given standard deviation in the magnitude, meaning that if you are much further down, it means that, okay, you have a star which is almost not pulsating, and it's only the largest amplitude at a given standard deviation which falls on the pink line. And to comment on the deviation observed in our Ursa Majoris or Mira itself, it's just that I mean the kind of pulsation associated with Mira is just not represented, was not represented in the sample of M-giant binaries that we studied. So it's a different physical phenomenon, and so that's why I mean we didn't dare extrapolating this pink line to the Mira themselves. Okay, I mean for V Hydrae or SFE it worked, but not for our Ursa Majoris or Mira.
But Mira is hence in radial velocity much stabler than what you would expect from the pulses.
Okay, thank you for the interesting presentation. So you actually obtained orbital parameters for quite some AGB systems, is that right?
I'm sorry, could you repeat the question?
So you obtained the orbital parameters for quite a lot of binary AGB systems, is that correct?
Yes, for 8 star, from our 16 sample, we obtain an orbital curve for 8 star,
So
8 AGB star.
do you know for those stars what like the orbital separation is and if they are eccentric?
I didn't plot them in a period eccentricity plot, but we have some with low eccentricity and some of them with higher eccentricity, but I didn't have the value quite here.
But that's really interesting because we don't know actually if there are eccentric binary AGB systems. And I study them a little bit with the models. So if you have like proof that there are eccentric binary AGB systems, that's really interesting. You're going to publish that soon?
Thank you. Any more questions? I have one myself, actually, your Lomskargel spectrum. That looks surprisingly clean to me. Is it a standard Lomskargel that you used, or?
The Lomskargel from the light curve.
Yes.
Yeah.
Very low noise
will
level.
yeah, this one.
Yeah.
Yeah, that's a Lomskargel periodogram, so a classical Lomskargel periodogram. I think I've computed using Lomskargel function of Python. This one have not been cleaned.
Not being
No.
cleaned. And so
But,
don't you expect for those giants a 1/f component caused by the granulation in the photometry?
by the what? I'm
By
sorry?
the granulation.
Maybe, but in fact, maybe there is aliases, but the two period is really high, so maybe the aliases are just smaller on the picture. But yeah, I don't know. We only, as I said, we only see the two period here and the third periodic pattern, which is really small on the picture here, but when we remove the 2-1 is the dominant one. But
Okay.
no
Thank
other
you.
pattern. But maybe this is due because the spanning is really high. We have 1 century of observation, so a lot of observation, which can give us those nice peak.
Okay, thanks. If no more questions, then I would like to thank Léa again. Thank you very much.
Thank you. Stop. Okay. Perfect. I think, do I need to